once again want to thank everybody for coming. It's so nice to see so many people in person again. We really appreciate that. I know we have some people watching from home, so I want to welcome all of you who are also watching us from there. I want to thank the Huntington, as always, for hosting us. It's always a great to be back in this auditorium. And I want to thank the Norris Foundation, which provides financial support for this series for many years now, and we really greatly appreciate that. So with that, I guess we'll get started. As many of you know, if you saw the advertisement, this is the 20th anniversary of this series. I'm curious if anybody has been coming the whole time. Are there some of you who really been here the whole time? You'll remember. With portable seats. And then we moved around a bit. We went to a few other places while the Huntington was building this. So it's really quite remarkable to see that this has been 20 years and here we are. So when we were planning the 20th anniversary, we decided it might be fun to bring back the original 4 speakers from that first year. And so that's in fact what we're doing. So each of the talks you'll get to hear from somebody and hear kind of what has happened over the last 20 years in the field they're going to talk about. Now, I was one of those original 4 speakers myself, and I talked about collisions between the Earth and asteroids. Thankfully, not much has happened in that field over the last 20 years. So I decided I better change topics. And instead, I decided I would just do a little preview or a kind of my highlights of the last 20 years or so in astronomy. Now, when I sat down to do this, it turns out that's a pretty complicated task. A really lot of great astronomy has happened over the last few decades. So I'm just going to highlight the few areas where I think are perhaps most interesting, at least to me. And you'll hear about some of these other topics from our other speakers as we go through the series. I'm doing that. That doesn't do it. I have to do this. OK. So before we talk about the 21st century, let me just remind you where astronomy was at the end of the 20th century. I almost put a picture of me from grad school in 1994, but thankfully I couldn't find it because I thought that would be kind of cute to show. I finished my PhD in 1994. I came to Carnegie as a young postdoctoral fellow in 1994. And this was a really exciting time to be a young astronomer because we knew astronomy was going into what we call its golden age. And in fact, as I'll argue tonight, the last 20 years really has been the golden age of astronomy. And that's partly because of new facilities that were coming online. A few of these started in the 90s, and these are the ones that are most obvious. The first, of course, is the Hubble Space Telescope, which was launched in 1990. It's been a long time for the Hubble. Now, you'll all remember, of course, that the Hubble had problems with its optics. And so, in fact, if it wasn't for the repair missions with the shuttles, we would never have really seen Hubble's true potential. And I would argue, in fact, that the main work with the Hubble Space Telescope really didn't start going until around 2000, once we had repaired it significantly. But the other development was the birth of big ground-based telescopes. And these are the Keck telescopes here in Hawaii. They were the first of this new generation of large telescopes. These are 10-meter mirrors. These are really large mirrors in individual pieces, as you probably know, in segments. But what was remarkable about this is that these were the first new big telescopes, really, since 1949. And that one in 1949 was the 200-inch down at Palomar Observatory. So astronomers had waited a long time to have a big leap in the size of their telescopes, and that came with the Keck telescopes. And so as the 90s were coming to an end, this was just the beginning. And we knew we were headed to really the golden age, as I said, for several reasons. But the real reason in my mind the last 20 years has been so interesting is this is really the first time in human history we've been able to look at objects across the electromagnetic spectrum. So the electromagnetic spectrum is just the whole spectrum of light. It's all the types of light. This is a beautiful example here. This is the Crab Nebula. This is the remnant of a star that exploded back in 1054. And what you see here is you see this nebula taken in various types of light, from the very low energy radio waves all the way up to the very high energy X-rays and gamma rays. And each one of these types of light tells you something different about an object like the Crab Nebula. And this is why the last 20 years has been so important, I think, because for the first time in human history, we've been able to observe things across that entire electromagnetic spectrum. Now, just to remind you, you're very familiar with the electromagnetic spectrum, even if some of those terms don't sound as familiar as others to you. But all of these types of light are used in our everyday life here. We, of course, have radio waves, which gives us our radio and TV. Microwaves, we all are very familiar with from your kitchens, most likely. Warm sources produce infrared radiation. And so an example here is a radiator. Another example is a human being. Human beings actually produce, you glow infrared light. Visible light, of course, is like the sun and lights. Ultraviolet we're familiar with because it, of course, damages our skin. We don't like too much ultraviolet. And X-rays and gamma rays are used a lot in medical work, as we know. X-rays have high enough energy that they penetrate your skin, but not the bones. That's why we use them to see bones. And gamma rays are really used very limitedly to kill things like cancer cells. Anyhow, all of this light, they're just different energies of light, basically. And the universe, objects in the universe, produce light across this entire range. And prior to about 20 years ago, we were stuck to look at just that little visible range in the middle. And that's what the truly remarkable revolution has been over the last 20 years. Now, why is that the case? Well, the reason is because we live on a planet that has an atmosphere that absorbs most of the radiation from the universe. And this is a plot just showing you, at the top, you see the various types of light, and then you see how far down into the atmosphere it gets. And what you'll see here is that the Earth's atmosphere, thankfully, scatters and absorbs most of the gamma rays and X-rays and ultraviolet radiation. We wouldn't want that radiation reaching us here on ground. Visible light, thankfully, gets through. That's why we look and we can see, and our eyes have evolved to look in that range. And a little bit of the radio wave get through. And so prior to about 20 years ago, if you wanted to do any of these types of work, you really do need to go to space. And that was really the limitation. Now, people at NASA realized this quite a long time ago, and NASA was preparing for this by launching its 4 great observatories, and these are them. And they all came around 2000, which is why this is the golden age of astronomy. There was the Compton Gamma Ray Telescope, which looked in gamma rays. There's the Chandra Space Telescope, which is still in orbit. This is an X-ray telescope. I use this one quite a lot in my own career. And I often refer to Chandra as the X-ray version of Hubble. It produces high-quality images in X-rays. The Hubble Space Telescope, of course, is in space. That's why it's the Space Telescope. But what you may not realize is although it is a visible light telescope, it also goes a little bit into the infrared, and more importantly, really, it goes into the ultraviolet. And so it allows us to see some light we couldn't see from the ground. And the Spitzer Space Telescope was an infrared telescope. Unfortunately, its mission has now ended. But these telescopes all came around the turn of the century and brought a real revolution for us. At the same time, astronomers on the ground were really, really busy building telescopes. I mentioned those Keck telescopes. Those were just the first of a whole series of new giant telescopes that were built. These were the first generations here. The Magellan telescopes are the ones we at Carnegie built at our Las Caponus. And you'll see the Gemini telescopes were an international collaboration. The very large telescope is actually 4 in Chile for the European Jews. And the Subaru telescope was the Japanese telescope that's in Hawaii. And all of these telescopes, and even more that came later, all of a sudden astronomers went from having just a few old telescopes to having this huge number of telescopes. And even on the ground, we, of course, also had some progress in the radio. This is, of course, ALMA, which is the huge array up in northern Chile. And this telescope uses 66 individual antennas to produce the most powerful radio telescope. And so all of these resources really make this a special time to be an astronomer. There's some other additional things that happen, and this is one that I think is really the most important. Astronomers have boy, it's really hard in COVID, after COVID to talk. I don't know, does anybody find that? Plus, it's my bedtime. I'm usually asleep at 7:45 now. Anyhow, let me start over. There's also been a series of very important surveys called the Sloan Digital Sky Surveys. It's really, as I'll show you in a minute, 5 different surveys that started in 2000 and are continuing today. And these surveys have had a real fundamental change on how we do astronomy. And so this survey was primarily done initially with a telescope, a 100-inch telescope in New Mexico at Apache Point. Now, a 100-inch telescope is not very big. All those telescopes I just showed you before were much, much bigger than that. I'll remind you, Edwin Hubble used a 100-inch telescope up at Mount Wilson in the 1920s for his important work. The Sloan telescope's not a big telescope, but it was designed to look at very large patches of the sky and to work in a very different way than other telescopes. So rather than individual astronomers using this telescope was used just to basically do a giant survey, basically imaging most of the northern hemisphere sky. And then after it imaged this huge patch of the sky, it then took spectrographs and actually measured spectra. That is, took the light and kind of looked at it in detail. You can measure, for instance, the redshift of these objects, the distance, the temperatures, all these sorts of properties. for millions of objects. And so on the right here, you see an example. This is some of the work from the original Sloan Digital Sky Survey. What you're seeing here is you imagine the sun is kind of there in the middle, and as you go out along these slices, you're going further away from us. And this is just one portion of the sky, and this is the opposite area of the sky, a fall sky and basically a spring sky. And what you see here, every dot on this image is a galaxy. And with this survey, they basically measured the distances of millions of objects. And what you see here is you see galaxies actually occur kind of in clumps and not kind of just randomly distributed. So this was really important work, but more important in my mind is the way this survey has worked. Because in the case of, for instance, those Keck telescopes, the Keck telescopes were built by our colleagues at the University of California and Caltech. And so in that case, University of California put in a big chunk of money, and Caltech put in a big chunk of money, many, many millions, and built these telescopes. And those Keck telescopes are used by astronomers at UC and Caltech. Similarly, our Magellan telescopes were paid for largely by Carnegie, and Carnegie astronomers uses that. For the Sloan Digital Sky Survey, it was a very different model. Rather than have one dominant partner build the telescope, you just have a whole bunch of tiny partners. And everybody contributes just a little bit, and they all adds up to the same amount you need to build the telescope. And so, for instance, you can join the Sloan Digital Sky Survey if you're an individual astronomer for often $100,000 or $200,000, which is a very small amount of money in astronomy. And you buy into the survey. So that was the first thing. It allowed, basically anybody in the world could buy into this survey for a small amount of money. So that was quite different than the classic model. The second thing is, unlike a telescope like Magellan or Keck, the astronomer doesn't go to the telescope and decide what they're going to do. There's a set program, and you buy into the program. And so, in fact, if you're the astronomer at home, you can sit at home. Somebody else is taking the data for you. Somebody else is reducing the data for you, and they put it online, and it's ready to go, and you just write your papers. And so this is a very different model than we've had here in the past. And in fact, it's become a really important model because what it has allowed people to do is it allowed people to be at very small universities and participate in astronomy. Places that couldn't spend millions of dollars to build telescopes like we do at Carnegie and Caltech can now participate in this survey. The interesting thing about the survey is this last point to me, the other fundamental difference. If you pay to join the survey, you can then be on all the papers that are written by the survey. So, you have to do something, but you don't have to do much often. What this means is that unlike Edwin Hubble, who wrote most of his papers, if you look at Edwin Hubble's papers, it's often Edwin Hubble, and that's it. In this case, for Sloan papers, you often have papers that have tens or hundreds of authors on it. So it's really changed the way we do astronomy. And so this has just been a very interesting sociology component over the last 20 years. I was going to end. I wanted to say the Sloan Digital Sky Surveys are still going on, and the fifth one started just last year. And this one's interesting because it's going to have a northern and southern component. And in fact, Carnegie is leading the southern component here. We'll be using our DuPont telescope at Las Caponus to image and take data for the southern portion of the sky. And this is being led by Juno Kohlmeyer, who many of you will know. She's given many of these Huntington talks through the years. Okay, so that was just kind of an introduction for why the last 20 years is interesting from an astronomer standpoint. This huge number of resources coming online, allowing us to do things that we couldn't do any other way. So now let's talk about what we've done and what we've learned. And so the first of these things, I'm going to call this section Watching the Universe Evolve. And this is really fun, and this is one of my favorite topics. Next year will be the 100-year anniversary of the famous Edwin Hubble plate. Many of you have heard of this plate. Some of you may have seen it. It's hidden in our vaults back on Santa Barbara Street. And this is the famous Var plate. What Edwin Hubble did is he used this plate to measure the distance to the Andromeda galaxy. So that fuzzy thing you see there in the middle of that image is in fact a galaxy, but people were not aware of that at the time. What Edwin Hubble showed was that this was a very big system, like the Milky Way, just very, very far away. I often refer to that plate as the discovery of the universe, in some sense, in that image. What has happened with the Hubble Space Telescope, appropriately named after Edwin Hubble, is this has allowed us to take these galaxies and study how they looked in the past. And the way it's done this is through a series of very beautiful and important images called deep fields. This is my favorite. This is, in fact, the deepest image ever taken with an astronomy telescope. This is called the Hubble Ultradeep Field. It was taken in the early 2000s. So let me just tell you a little bit about this. The way this image was taken was basically a region on the sky was found that had no bright foreground stars, so it looked blank, so to speak. And then the Hubble Space Telescope was pointed over the period of a few weeks at that same spot, and a series of images were taken. They're stacked together to get a very, very deep exposure. And when you do that, the blank sky is no longer blank. It's in fact littered with little faint things, these little things you see in this image. And these little faint things are distant galaxies. Every dot you see in this image pretty much is a galaxy. And they're tiny because they're very, very far away, or we're seeing them way in the past. In this image, most of the objects you see, especially the smaller things, are being seen about 8 to 10 billion years in the past. That is, it's taken 8 to 10 billion years for that light to reach us. So the light we're detecting left those galaxies 8 to 10 billion years ago. This is an image, effectively, of what the universe looked like 8 to 10 billion years ago. That is truly remarkable to me. First of all, I think it's also the most beautiful image ever. I love this image. But let me remind you, the Earth is 4.5 billion years old. So this is an image of the universe 5 billion years before the Earth even existed. That's truly remarkable. And so as astronomers, we can look at these very, very distant galaxies and say, this is what galaxies look like 10 billion years ago. We can look at galaxies that are 5 billion light years away and see what they look like 5 billion years. And then we can look at Andromeda and the nearby galaxies and see what they look like today. And based on that, you can try to put this all together to try to understand how the universe has evolved. Now, sadly, it's complicated. Or maybe not sadly, we like lots of work. And the image already tells you it's going to be complicated if you spend time looking at this image, and I hope you're spending time looking at this image, because you'll notice that the galaxies have all different shapes and all different colors. And the shapes, you'll see some of them. I can see if I can find some of them. There's this one over here on the left here looks kind of like a spiral galaxy. That's kind of what we think the Milky Way looks like. You can see there's one up here that's kind of spirally. Then you have these other ones that are more like football shapes, that one there and this one there. These we call elliptical galaxies. You'll also notice that the colors are different in the galaxies. And so colors are very important in astronomy. They're telling you what types of stars dominate the image. And so the biggest, most massive stars that form are blue. And so when if you see a galaxy that's very, very blue, it means it's dominated by these massive stars. But the massive stars don't live very long. They only live millions of years. And millions of years is very short in astronomy. It sounds like a long time, but it really is. And so if you see a blue galaxy in this image, you're seeing a system that at that time was rapidly forming stars because it's so blue. It has all these stars that don't live very long. As opposed to the red stars, which live for billions of years, 10, 20 billion years. And so if you form a galaxy, it forms the red and blue stars kind of all at once. The blue stars will dominate because they're so bright. The blue stars will eventually die, leaving behind the red stars. So if you see a reddish galaxy, you're seeing a dead galaxy in some sense. It's one that's no longer forming new stars. So the question is, why are they not forming stars? And that's where it gets complicated. So I'm not gonna have an answer to that because that answer is very complicated and we still don't know it fully. Let me just point out something though. I should have pointed this out early. As always, I end up ad-libbing my talk. I practice it for a whole week and then I end up just going in completely different directions. Anyhow, but let me just show you. This is the Hubble Ultradeep Field. That is that image I just showed you. It's a little bigger than the one I showed you. But I just want to compare that to the moon. Because this image, if you do the full size of it, it's a little bit bigger than the one I've plotted here, has 10,000 galaxies in it. And that's 10,000 over that tiny little region there compared to the moon. And so, in fact, if you extrapolate across the whole sky, you estimate that there's 1 trillion to 10 trillion galaxies in the universe, each with billions of stars and trillions of planets. The universe is truly immense. That's the lesson from that one. Now, you can go even further with this deep image, and this is some work that Evo Labay, one of our former Carnegie postdocs, did. Around 2010, there was the last repair mission for Hubble went up and had a new infrared detector on it. This allowed us to take deep images in the infrared. And so Evo used that, Evo and his collaborators, to take a deep image of that same region of the sky in the infrared and added that to the optical light. Now the infrared is important because as the universe expands, Objects get redshifted. That means their light actually shifts further and further to the red. And for the most distant objects in the universe, they're so far away, their light has shifted out of the visible range into the infrared. And so by adding that infrared, Evo found some galaxies that are even further away. These objects were seen 13 billion years ago. The universe is about 13.8 billion years. That's when the Big Bang happened. So we're seeing objects within the first billion years of the universe. This is truly remarkable. One thing I like to point out about these little galaxies that Evo has found is they're very tiny. They only have about 1% the mass of a galaxy like the Milky Way. These are not really fully formed galaxies. We're seeing galaxies really kind of forming the first things that are going to end up being galaxies. And I don't know how many of you saw, but there are even a few things even further away that are known by Hubble. This has been the longtime winner for a while, GN's Z11. This thing is being seen 13.4 billion years in the past. And then just last week, this was just announced on the news. I don't know if you saw this. There's a new thing called HD1, which they believe is 13.5 billion years. So this is right now the record holder, the furthest thing we've seen. I put a question mark because this really, I just saw the press release. I don't even know, I haven't read the paper yet. And so obviously we want to kind of confirm this. But we're really seeing kind of the very, very first things that formed. Now this is a great plot. This will kind of show you how much we've learned over the last 20 years, and 30 years actually. And so what this is this shows you various timelines. And this shows you basically how far back into the past we've gone. So right back here would be where the Big Bang happens over here. And you'll see that when I was a little grad student in 1995, we could see about 6 billion years back in time. That sounds like a lot. It is a lot. That meant the Earth hadn't even formed even at that point. But the reality is, if you look at the data, what you see is that there's very little happened in the last 6 billion years. All the good stuff seems to have happened before that. And in fact, that we wouldn't have even known until here's that Hubble Ultradeep field. So you see how much further it went out than that. It's going out only 800 million years after the Big Bang. And then this is Evo's work here, which is about 480 or 500 million years after the Big Bang. So we're seeing things within the first 500 million years of the Big Bang with Hubble. Now, the problem is you can't go all the way back with Hubble because it's not an infrared telescope. And as I said, as the universe is expanding, those faint initial galaxies are getting redshifted into the infrared. And so what do? You launch an infrared telescope. And so you almost all have certainly heard about the James Webb Space Telescope. It has been all over the news. You know when they do a story on 60 Minutes that you've really made it big in astronomy. So I don't know how many people saw that, but that was a really good story. Anyhow, so the James Webb Space Telescope, the primary driver for this telescope, or one of the two primary drivers, was to push back way to the very beginning and see those first stars and galaxies. And I don't have to say any more about it because we have a whole lecture on it 2 weeks from tonight. And this lecture is by our own Alan Dressler. Alan played a really important role. He chaired the initial committee that came up with the idea for the James Webb Space Telescope back in 1993. So it is almost a 30-year journey to get us to where we're at today. So you're going to hear all about James Webb and the exciting things it's going to do in 2 weeks. So please come back for that. Okay, so we've learned about the evolution of the universe a little bit. Another area I think we've made a huge amount of progress in the last 20 years is this understanding the nature of black holes. Black holes are always complicated. They don't have to be that complicated, but we've really learned a lot about them. I'll remind you, a black hole is just a region of space that has such strong gravity that nothing, including light, can escape it. And so astronomers know of basically two different types of black holes. I'm going to talk about the first type, and then I'll get back to the second type a little bit later. The first type is what we call a stellar black hole. Stellar means star, and so these, in fact, are black holes that are the product of the end of a star's life. And so we believe these form when very, very massive stars die. I'm not going to go through the process. This is the process for a massive star. I'll just pick it up here. When you have a massive star that's near the end of its life, it ends up in a giant explosion we call a supernova. In the process of most of the star getting ejected on the supernova, the core kind of has a counter movement that comes down and crushes it deeper and deeper. And so the core collapses. And if that core that's left over has more than 3 times the mass of the sun, we believe it will collapse into a black hole. Now, if it has a mass less than 3 times the mass of the sun, it collapses into another interesting object called a neutron star, and I'll talk a little bit about neutron stars. So we've known that these sorts of black holes might exist for a while, and in fact, it's almost 60 years since the first evidence of them. So I thought it's important to say, how do we know about black holes? You can't see them, and it is true you can't see the black hole directly, but what you can see is you can see the things around the black hole. And in fact, in 1964, there was a rocket experiment that went up and found a very, very bright X-ray source on the sky in the constellation of Cygnus. We nicknamed it Cygnus X1. That means it's the brightest X-ray source in Cygnus. Astronomers can be exceptionally creative. And what was Cygnus X1? Well, what people realized is that Cygnus X1 was an X-ray source in a binary system. There's a big star that we can see its visible light, and then an X-ray source coming from the other place without the star being visible. And so what this is, in fact, is if you imagine you have two stars that are living around each other, they're orbiting, and one of them blows up in a supernova explosion and becomes a black hole, then you have a black hole and a regular star kind of in this orbit. And that's really what happens. Eventually, the other star will puff up as it gets later in its years, and if it puffs up big enough, the black hole will start stealing material from it. And that's what this artist's drawing shows you here. You can see this is the second star, and this black hole here is stealing material. And as that material comes towards the black hole, it swirls in, heats up to very high temperatures, and produces the X-rays. And so in fact, black holes, you don't see the black hole itself, but you can see the region around it as the material swirls in. And so this was how we first knew about black holes. And in fact, by the turn of the century, we already knew, the turn of this century, we already knew of about 15 of these X-ray binary systems. They were really the best evidence we had for black holes. But of course, a lot has happened here. And there are other ways of finding black holes. And the most interesting, of course, gets back to Einstein and the theory of general relativity. Here's just a wonderful picture of Albert Einstein visiting Carnegie Observatories in 1931. And what, of course, Albert Einstein said was that in general relativity, gravity can be thought as the curvature of space-time. And what he said was, what this means is that the more massive an object is, the more massive that curvature is going to be. So this is a drawing of a very inaccurate drawing here. The moon and Earth, the moon is much bigger relative to that, but it's still smaller than the Earth. And you can see that the Earth has done kind of has a bigger dent in space-time than the Earth, than the moon, sorry. And so the following year, so he published that in 1915. In 1916, he wrote another paper that showed that out of general relativity came the idea of gravitational waves. And so what basically Einstein predicted from this was if you have two massive objects that are accelerating towards each other, they will produce ripples in that space-time that can be detected. And this is, it's really hard to see. They are black holes, so there's a black hole there and there. I don't know if you guys can see it. From my angle, it's very hard to see. But imagine you have two black holes that are accelerating towards each other. You'll see the green you see here. These are the gravitational waves. As their orbits decay and they get closer to each other, they accelerate more rapidly, and you'll see the green, the waves start getting more and more intense. And eventually they're going to merge. There they go, and you get this very bright event in the gravitational waves. Well, if that one didn't come out, this one's probably going to be even worse. And what these gravitational waves do is, in fact, the Earth is continually getting bombarded by them. You probably can't even see them. I don't know if you can see them. The green waves are kind of coming from this direction. That's supposed to represent the gravitational waves. Now, this is happening all the time. Now, thankfully, it's just vastly exaggerated. I think that might be a slight underestimate. I would say, I don't know what's bigger than hugely, it's very much exaggerated. But it is true that the Earth is continually getting bombarded by these gravitational waves as these events are happening throughout the universe. And what they do, if you saw that, and you can see it in the simulation here, is you kind of get a stretch and a pull on the Earth. And so, in fact, as most of you probably know, we now have been able to detect this thanks to our colleagues at Caltech and MIT and this amazing facility known as LIGO. LIGO has basically these two units that are one in Washington State and one in Louisiana. And the idea here is it can detect extremely small motions. This is the measure of the motion here is so small. It's 10,000 times smaller than the atomic nucleus. This is truly incredible. And as you probably all know, in 2016, they detected this for the first time. So here you see these are the waves coming through, and you can see the two detectors look identical. And so this was really, in 2016, this was really another proof of general relativity, but also very exciting because this was the first time we had actually had evidence of two black holes that had merged together. Now, the really interesting thing, though, were the types of black holes. From the data, the LIGO scientists can model this and figure out what the masses were of the black holes. And when they did this, they found that one of these was 26 times the mass of the sun, and the other black hole was 36 times the mass of the sun. Now, the reason that's interesting is prior to LIGO, we thought that these stellar black holes got to be about 20 solar masses. So these were already, both of these black holes are bigger than the black holes we thought existed. And this is a really nice diagram that kind of shows that. This is, basically these are all dead things, dead stars. And as you go up on the plot here, this is solar masses, so this is the mass times the sun. The purple things, you see these purple things that all kind of fall in the middle, you'll see they run from about 3 to about 20. These purple things are these X-ray binaries, these things that I told you we knew about for a long time that indirectly provided evidence of a black hole. And you'll see that they kind of do peter out about 20. This one with the question mark is kind of the most massive. But the blue things here are the black hole mergers that LIGO's finding. And in each of these cases, so let's take one here on the left, you'll see the 2 initial black holes, and the arrow points to the merger product, which of course is some combination of those. And what you'll see here is that the LIGO black holes are almost all above 20 solar masses. And so what this has told us with LIGO, in fact, the biggest one, I think this one here, one of these is like almost 80, maybe even more than 80 solar masses. And so what LIGO is telling us is there are big stellar black holes that we had no idea about prior to about 5 years ago. And why? And how are they made? And we don't really have a full understanding of that, and there'll still be many more studies, but they're really, really interesting. I'll just point out here, at the bottom here, you have our neutron stars. As I said before, if the massive star blows up and the mass is less than about 3 solar masses in the core, you get what's called a neutron star. These are very dense old stars. And there's a bunch of these. The yellow ones are ones we knew about. We've known about neutron stars for quite a long time. But of course, the really exciting result with LIGO came in 2017. And many of you have heard this so many times from me that I kind of didn't want to mention it, but I kind of had to. And for the first time in 2017, LIGO detected a merger of 2 neutron stars. Now, what's interesting about that is when the black holes merge, we don't think there's a light signal. At least we haven't found a light signal. Every time LIGO finds 2 black holes that merge, we take our telescopes and we try to scan the sky and find something. But we haven't seen a light signal, and we think there probably isn't a light signal from the black holes. In the case of 2 neutron stars, we know there's a light signal, and we detected it back in 2017. I have to drink some water here. This is the discovery data from Las Caponus. What you see here, this is the neutron-neutron star merger, the light from it. And just because people seem to be very confused about this image, this thing here is the galaxy, excuse me, is the galaxy. This object actually is part of that galaxy, it just is at the edge of it. So the neutron star merger happened in that particular galaxy. These are the team of the people from Carnegie who were involved in that discovery, and you've heard all of them have given Huntington lectures before. I'd just like to point out, because 2 of the science papers were written by Maria Drought and Ben Shappy, who were postdocs at the time, and have now gone on to be faculty members. And Tony Pirro and Josh Simon, who many of you know, are currently faculty members at Carnegie. And the reason why the neutron-neutron stars mergers are interesting, really, is because we believe this is the source of some of the heaviest elements in the universe. This is your old periodic table from high school, where it's now labeled by where the element comes from in the universe. It's really quite interesting. And these neutron-neutron star mergers, we think, are all these purple things down here. So there's platinum and there's gold. So we think that you need these very massive mergers of these very dense old stars to form those elements. I just point out that this is a human figure, of course. What you see here is about 3/4 of you is orange. And that orange comes from nuclear synthesis in the centers of stars. And so when you hear, we are stardust and blah, 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 you really are. 73% of you comes from the centers of stars. And I like to point out, like now when I'm tired and want to go to bed, that 10% of you is actually hydrogen. And that hydrogen comes back from just after the Big Bang. So 10% of you is almost 13.8 billion years old. So I have a reason to want to go to bed at 8 o'clock on a Monday night. But I won't. Okay, let me get some water here. Okay, so that was the stellar black holes, and LIGO has really been a revolution in that field. But there's another type of black hole which is kind of equally interesting. These are called supermassive black holes, and these are black holes that are 1 million to 1 billion times the mass of the sun. So these are much, much bigger than the ones I just talked about. And what's interesting about these is that we now know, over the last 20 years that pretty much every big galaxy in the universe has one of these black holes at the center. Now, we don't know why. This is really going to be a very important field of study. The fact that every galaxy seems to have one at the center says that this must be fundamental to how galaxies themselves form. But we don't know yet. We don't quite understand that. Now, we've known about these for quite a long time, too, because because in this case, just like the stellar black hole, as material swirls into the black hole, it produces a lot of energy, in this case even more than those other black holes I talked about. And these are what we know as quasars, so that's a little artist's rendition of a quasar. And so to find these black holes, once again, you can look at them by looking for their bright X-ray emission particularly. This is another nice image. This is taken with the Chandra X-ray telescope. So this is the same field that I showed you earlier in the first part of the talk, the Hubble Ultradeep field. In that case, I showed you all the beautiful colors and the light. Now, in that image, with Hubble, you were seeing the stars in the galaxy. That's what produces the visible light. Those same galaxies, those stars don't produce hardly any X-ray emission. So if you point an X-ray emission of those galaxies, you don't see anything unless they have one of these black holes in them. And so what you're seeing in this image, every little speck in this image, is basically one of those black holes at the centers of those galaxies that's being lit up by material falling into it. And then once again, it's a tiny little patch on the sky, and you see there's a lot of black holes. So these are all these supermassive black holes, these things that are 1 million to 1 billion times the mass of the sun. Okay, so we know a lot about these black holes. This is one of the most spectacular results. I don't know if there's anything more spectacular than this, by my colleague Andrea Getz at UCLA. Many of you probably have seen this. And this is a great time series. So up here you see the time that she's taken the data, starting in about 1995, going up to about 2 or 3 years ago. What you're seeing here is very high-resolution image of the center of the Milky Way galaxy. And what you're seeing here are the motions of individual stars. And you'll notice something quite interesting about them. The center of the galaxy is marked by this white star here. And so you'll notice as objects come by the center that they whip around really rapidly. Look at that one there. And the reason they're whipping around rapidly is because there's a very, very strong gravitational force at the center that they're feeling. And this strong gravitational force isn't producing a lot of energy. You don't see it. The white star's in the way, but if you take the white star out, there's nothing there. And in fact, you can do a calculation and show that the only way you can get the acceleration of these stars through the center like that is if you have an object about 1 million times the mass of the sun. And so in fact, this is, in my mind, really probably the best evidence we have for a black hole, or certainly one of the best evidence for a black hole. And the Nobel Prize Committee agreed. They gave her the Nobel Prize in 2020 for this work. And in fact, there's a competing team in Germany that also got the Nobel Prize. But this is really amazing. In our own backyard, not really our backyard, it's pretty far away, but in our own galaxy, we have a giant, don't get scared, we have a very nice black hole. Oh, I want to point something out here because somebody's going to ask me. You may be going, well, if there's a black hole there, why are the stars not falling into the black hole? Is that somebody thinking that? Yeah, somebody's always thinking that for good reason. And although it looks like they're getting very close, they're not really getting that close to the black hole. They're getting close enough to feel the acceleration, but not close enough to fall in. And so there's this misconception about black holes, they're very misunderstood, that everything gets sucked into the black hole. That's not really how it works. Gravity is very strong around the black hole, but once you've stepped away from it a bit, the black hole acts like any gravitational object. So in fact, if you replace the sun with a black hole, the Earth would continue to orbit that black hole. We wouldn't have a sun, but you'd still orbit. And so in this case, they're not falling in because they're really not getting as close as it looks like they're getting. Anyhow, still amazing work by Andrea. Now, of course, there's this other amazing result from just a couple years ago, which was the first image of a black hole. And I want to explain what you're seeing here. This is a nice little simulation that shows it. Now, imagine you have a black hole, and there's that black hole. You can kind of see it. And you have light being created all around the black hole. Stuff is accreted onto the black hole and producing light. And now if you view it from any particular angle, you're going to see what you basically see in that image. I don't know if people have seen this before. Let me see if I can go back and play that again. Did it do it? No, it didn't do it. There we go. So what you see, if you watch it, you'll see light coming from all different directions, and that light is getting bent around the black hole. And so from our viewpoint, we're basically seeing all the light is coming from various directions and kind of backlighting the black hole in some sense. And that's really what you're seeing in that image. Now, this image is truly spectacular, and to do this, you really needed to combine light from telescopes across very large distances. The large distance allows us to see things on very, very high resolution. And so this is called the Event Horizon Telescope. It's not a specific telescope. It's an array of telescopes that all work together to resolve that structure. And so this one that they found in the 2019 one is very, very bright. It's in a nearby galaxy called M87. There's only one other black hole that they actually can probably do with this current array of telescopes. And that one is the black hole at the center of the Milky Way galaxy. This is the same one that Andrea Getz has studied with those individual stars. So the question is, can we get a picture of our own black hole in the Milky Way? And if you asked me 3 years ago, I would have said yes. But the answer is I haven't seen it yet. And so as far as I know, there must be a problem. It probably ends up being very, very complicated. In the case of the image that you've seen, this is a galaxy that we know it's almost a quasar. It's actively, lots of stuff is falling on it, and it's glowing very much. In the case of the Milky Way one, it just is kind of quiet, and so maybe there's not enough light to see the effect. I don't know, but hang on tight. Hopefully we'll see another image of a black hole sometime in the next few years. Now, for the stellar black holes I talked about earlier, we know they're the end product of stars. Where do the supermassive black holes come from? Well, we don't know, but we're getting some important clues. And one of the most important clues has come from work by this young guy, Eduardo Benedos, who many of you will know. He was at Carnegie for many years. Eduardo has become the expert at finding the most distant black holes in the universe. He's now found several that were seen over 13 billion years in the past. This is almost back to the same part with those galaxies I was showing you. Basically, his black holes he's finding are at that same distance. This means he's seen full supermassive black holes, things that are 1 billion times the mass of the sun, a few 100 million years after the Big Bang. And this is really surprising and shocking and quite honestly not understood. How do you form such a huge black hole so soon after the Big Bang? We don't have an answer for that, but I think the answer, what it's telling us is that this has to happen almost instantaneously soon after the Big Bang. And so this would be a huge field, and once again, James Webb will help here, because James Webb will probably find many of these very distant black holes. But we don't really know where they come from, but we will hopefully soon find out. Okay, my third topic is exoplanets. So I'm kind of moving from the edge of the universe to the closer things. And so this is a field that has, to say it's been explosive growth is an understatement. So an exoplanet is a planet around a star other than the sun. When most of us grew up, we knew of 9 planets, right, in our solar system. And in 1992, we found the first exoplanet. So that was the first planet outside of our solar system. This plot is remarkable. This shows you the number of exoplanets found by the year, basically since 1992. And what you'll see here is that in the year 2000, we knew of 32 exoplanets, which was a good number, but not very many. As of today, we know of 5,009. And so if you feel like when you're reading the news, every 3 days there's a story about a new planet around some star that's doing some weird thing, it's true. It really is. Astronomers have put so much effort into finding these exoplanets, and we now know of over 5,000 of them. This is truly remarkable. Because when you have that many, you can start asking what their properties are and things of that sort. And this is a plot I like quite a bit. This is a plot which shows the orbital period, that is how long it takes this exoplanet to orbit its star. So in the case of the Earth, it would be 365 days for us. And then as you go up on this plot, you're going towards the bigger things. So the small planets down here and the big planets up here. And you'll see I've kind of labeled some different types of planets that one sees. The first planets that were found with the first exoplanets that were found were things called hot Jupiters. And like their name says, they're like Jupiter but hot. And they're hot because they're near their star. So in our solar system, the inner planets, the terrestrial planets, Mercury, Venus, Earth, and Mars, are all rocky planets we live on. And then the gas planets, the big ones, are all in the outer part of the solar system. These hot Jupiters, imagine if now Jupiter was in the place of Venus, or Jupiter was in the place of Mercury. That's what these hot Jupiters are. They're big giant gas giants sitting very, very close to their sun. That's pretty weird. Lava worlds are rocky planets like Mercury or Earth, but that are so close to the surface of their star that they're almost molten or possibly molten. Really, really unpleasant places to live, to say the least. The rocky planets here are things more like we're familiar with here on Earth. And then we have a whole series of planets that we think might be covered in oceans or covered in ice, all sorts of planets. I'll point out one thing we don't see, and you can see, by the way, here's the Earth, Neptune, and Jupiter. What we don't really have the capability of seeing planets like the Earth yet, so the Earth is this thing here, I think, and, or should be close to that. We don't really have the ability to see planets like the Earth that are far away from their stars. The planets that we see like Earth are very, very close to their stars at the moment. But we're going to get there. This is 5,000 exoplanets. That's pretty good. Now, one of the interesting things, the primary technique used to find these exoplanets is called transit astronomy, or the transit method. And we're going to do that experiment right here. You're going to imagine I'm the star. You're going to imagine you're on Earth, and I have a planet coming around. And if things work out just right, from where you're viewing me, the planet will move in front of the star surface. When it does that, because the planet doesn't produce light, the star will get a little dimmer because the planet is blocking some of my light. And we can look for these dips and find planets. And that's, in fact, how the majority of these exoplanets we found have been found. Now, one of the great things about this method is that one thing that comes out of it automatically is the size of the planet. It's a math thing. You can trust me on that one. I'm not going to do that with you. And so that means for most of the exoplanets have been found with this technique, we know the radius of the planet, or the diameter of the planet. And if you plot that, this is the plot of basically those 5,000 planets as a function of, and the scale here is relative to the Earth, but the easier thing to do is up here see our solar system. And you'll see here's our rocky planets again. Now this is in order of size. So the smallest one is Mercury, then Mars, then Venus, there's Earth. And then here's our big planets, Neptune, Uranus, Saturn, and Jupiter. You'll notice something quite interesting. First of all, in the solar system, there's a nice little gap. Neptune is significantly bigger than Earth. There's a nice little gap there. The other thing you'll notice is that most of the exoplanets, the distribution here, peaks in that gap, which means most exoplanets in the universe that we've seen so far, at least, if this holds everywhere, are in fact bigger than Earth, but smaller than Neptune. We call them super-Earths, because we're once again very creative. You can call them sub-Neptunes. I don't think that's as exciting. I prefer super-Earths. But some people do call them sub-Neptunes. But the real interesting thing is, why are these the most common type of planet? Why does the solar system not have one? That's pretty interesting. But even more interesting to me is, what are they? Because these planets, these small planets, we all know are rocky. These big planets, we all know are big giant gas balls. What happens, and there's presumably some transition, maybe they're rocky for a while and then become gassy. It's really quite interesting. And if you want to ask the question, is there life in the universe, and you want to study planets to look for that life, you want a solid surface. So you want to know these most common types of planets, in fact, are rocky. We don't know, so we're doing that. It's very, very hard work, but we're trying to do it very slowly. The other thing you might want to know is you might want to know, are these planets in the habitable zone? The habitable zone is defined as the distance from a star so that there's liquid water on the surface. So we thankfully live in the habitable zone. It turns out that Venus and Mars are actually kind of on the edges of the habitable zone in the solar system. So we almost had 3 habitable planets in our solar system. And so the question is, how many of the planets are the right distance from their star that liquid water could exist? And once again, we think this would be a good scenario if we want to look for life. And I'll just point out, we actually know of a good number of habitable planets now. We have about 25. That's pretty impressive. These are them. Warning, when you see these images, these are not real images. We do not see the planets. These are drawings of what they look like. And you'll see their size relative to Earth. You'll see some of them, in fact, are probably these super-Earths. But you'll see we have about 25 planets that are the right distance from their star to potentially have liquid water on them. That doesn't mean they're necessarily good candidates for life. They may have other issues, other problems. But we are really making huge progress. And eventually, over the next decade, we're going to really want to understand the properties of these systems. Okay, now I could talk about exoplanets for hours because I love this topic, but I don't have to because our third lecturer is, in fact, Paul Butler, one of the world's experts. So Paul came from our Carnegie Earth and Planets Laboratory. That's our DC branch. And Paul was one of the creators of one of the methods called the radial velocity technique to find planets. And he was one of the first people to find exoplanets. And he will be here on May 9th to talk all about exoplanets. So please come back and hear from him. Okay, my last science topic is the solar system. So I really am working my way back home. This is an image of how we might have imagined the solar system looked If you asked me 20 years ago, what is the solar system? Well, the solar system has one big giant yellow star called the sun and 9 nice little planets. Well, as you probably know, that isn't the scenario we live with today. And the reason for that is because of the discovery of a whole bunch of smaller planets in the outer solar system. And this is really the first one. This is Eris, which is really the troublemaker for many planets. And this, what you see here, this is the discovery image. This is 3 images taken over time. That's the planet there. It's moving very slowly, but it is actually moving among those 3 images. This was found by Mike Brown, our colleague at Caltech. And when Mike found this back in 2005 and announced it, it was very exciting because this planet is actually more massive than Pluto. And so this was, right away people got excited. Was this the 10th planet in the solar system? Well, of course, that isn't how it ended up going down. The next year, all the astronomers got together in the International Astronomical Union. This is our big union that decides how we name things and things of that sort. And we decided that Eris, this is once again an artist drawing, should really be in a different class of planet. It really belongs in its own class, and we called it a dwarf planet. And in fact, because of this, because it's actually bigger than Pluto, Pluto also got demoted. And that was the part that caused a lot of trouble. Yeah, so I already see people mad, crossing their finger. And for 3 years, anybody, and I told anybody I was an astronomer, all I had to hear about, why did you do that to Pluto? I had one guy who actually thought Pluto had disappeared, which I really didn't know where to go with that one. But there's good reason that to call Pluto a dwarf planet, and this image here really shows it. We actually know of 5 official, we have 5 official dwarf planets. Here they are, these guys here. And several of them, including Pluto, have moons, which is really kind of cool. This is our moon, and this is Earth. And so I think it's pretty clear if you compare the size of these things to the moon, they're pretty small. And so the dwarf planet is, I think, an okay way to call them. Now, if you're really, really concerned about this, that Pluto's no longer a planet, we're not saying Pluto's no longer a planet. We're saying it's a dwarf planet. And if your solar system wants to include the dwarf planets, you are more than welcome to do that. But you have to add all of these 5 in, first of all. And in fact, there's probably hundreds of more like this that are being found. These are the 5 that we've all agreed are, in fact, our dwarf planets. And so at some point, you'd have to add potentially, as I said, 100 or 200 extra planets into your solar system. Now, you may be wondering, if Pluto's a dwarf planet, what does that make the Earth? It makes the Earth and the other planets, we now refer to them as classical planets. So the 2 classes of planets are the classical planets and the dwarf planets. Now, beyond this, of course, there are many more candidates, as I said, for dwarf planets. And one of our own astronomers, Scott Shepard, once again from our Washington, D.C. office, is one of the world's expert at finding these very, very distant objects in the solar system. These images are kind of hard to see. Sorry, they didn't come out very clearly. This is one here he calls Far Out. This one's called the Goblin. There's a new one he has called Far, Far Out, which is even further out. But for those of you, in case you can't see it, this orbit here is the orbit of Neptune. And you'll see this object goes way beyond the orbit of Neptune. These things are going to the outer reaches of the solar system. And so these were once again truly unexpected. And once again, if you want to, they are likely dwarf planets, so you have to include them in your solar system. Now, this of course led to a huge and very exciting, potentially exciting issue, and this is when Mike Brown and others plotted the orbits of those first 5 or 6 dwarf planets seen. They all seem to be kind of clustered in the same direction on the sky. They have an interesting inclination relative to other planets in the solar system. All of this suggests that they've somehow been perturbed, that their orbits have been altered by an interaction with something else. And so this interaction is believed to be Planet 9 or Planet X. That's, by the way, it's very controversial. Some people don't like to use the word Planet 9. But this just shows you an idea of what that would be. This would be a big planet in the outer solar system, well beyond Pluto. The interesting thing about Planet 9 is if you look at the orbits and you take them at face value and assume there is a planet there that's perturbing them, that Planet 9 would have a mass about 5 times the mass of the Earth. Which the reason that's interesting is that would probably make it a super-Earth. It would actually fall in that gap that I showed earlier with the exoplanets. It would just be at the edge of the solar system. So now the question is, does Planet 9 exist? Everybody's looking for it. We're looking for it at Carnegie. Our colleagues at Caltech are looking for it. I will say, as I'll talk about in a second, if we don't find it within 10 years, then I don't believe it exists. And I'll show you why in a minute. But before I do that, let me just say we do have a 4th lecture, and I'm not going to talk about cosmology because I already talking way too much. And so thankfully, we have a whole talk on cosmology by our former director, Wendy Friedman. We're super excited to have her come back. Now, as many of you know, Wendy is, of course, one of the world's experts on measuring the expansion rate of the universe. The interesting thing she's referring to here with the crisis in cosmology is recent different techniques to measure the Hubble constant are getting different answers that are inconsistent with each other in a way that implies, potentially, there's something new and exciting about the universe, some new physics we don't understand. So please come back on May 23rd to hear Wendy talk about this. It's a super exciting field. Okay, now I just want to talk briefly about some of the things that are coming next. We've had this golden age of astronomy, but what is coming next? I already mentioned the James Webb Space Telescope, and you're going to hear about this in 2 weeks. I don't want to go into much detail, but let me just say, if I'm back on this stage in 20 years, giving this talk, you roll me in. If I'm giving that talk, I'm almost guaranteed to be talking about the James Webb Space Telescope. There's really no question. It's going to have impact on that very distant universe. It's going to allow us to see those first stars and galaxies. It's also going to be very interesting for studying exoplanets, and Alan will talk all about that next time. So for sure, in 20 years, we're going to be talking about the James Webb Space Telescope. But there are some other interesting ones that you may be less familiar with. This is one that's coming online very soon. It's the Vera Rubin Observatory, named after our famous Carnegie astronomer Vera Rubin. This was formerly called the LSST, in case you're familiar with that term and didn't realize we've renamed it the Vera Rubin Telescope. This is a telescope just very close to our last Caponus Observatory, in fact. But this telescope is dedicated to imaging the sky. And so what it will do is it will basically image the entire southern sky every 3 days. And the idea is if you keep going back to spaces and you repeat it, you can look for things that have changed, particularly things that blow up, like supernova. But this is why I made the comment about Planet 9. This thing had better find it, right? Because this is a big telescope imaging basically the entire region of the sky it should be in. And so, in fact, if we haven't in 10 years with the Vera Rubin telescope found Planet 9, then I don't think it exists. But that's me. I'm not speaking. Maybe Scott and Mike Brown will disagree with me, but that's my take. LIGO is also getting a significant upgrade in 2024. And it's going to go, at this point, it's going to detect a gravitational wave event a day. Right now, with its current form, it's every couple of weeks it sees one. So this is a huge increase. We're going to see more of those neutron-neutron star mergers, black hole mergers. That's super exciting. There's another one coming up you may be less familiar with, which is the Nancy Grace Roman Space Telescope. This used the spare mirror from the Hubble. They had some mirrors left over. It's the same size as the Hubble Space Telescope, but this one is being built in a way to emphasize doing imaging over very large areas of the sky, so a much bigger field of view than Hubble. And this is going to be very good for studying, for instance, dark matter and dark energy. I want to give a shout out to Nancy Grace Roman. You may not know that name. She was an early scientist at NASA who actually really was responsible in many ways for the Great Observatory program, which I mentioned at the beginning. So all this Hubble and Chandra and all these telescopes, she was very much responsible for that. And so she's being honored with this telescope being named after her, hopefully in 2027. And then on the ground, of course, we have our giant telescopes, and this is going to be super exciting. There are 3 of them. This is the European Extremely Large Telescope. That one will be in Chile. This is, of course, our own giant Magellan telescope. That'll be at our Las Caponas. And this is the 30-meter telescope that our colleagues at UC and Caltech are building that will hopefully be in Mauna Kea. As many of you probably know, there's a lot of issues with that particular potential site. But these telescopes really will impact all areas of astronomy. But I really want to start by just giving you a sense of the huge leap we're making from our current telescopes to these telescopes. The biggest telescopes we have on the ground right now are maybe a little bit bigger than one of the mirrors on the giant Magellan telescope. So this is a huge leap in technology. And what happens when you have a huge leap in technology in astronomy is you discover a whole bunch of things you were not expecting. These are just going to be super, super exciting telescopes. In case you haven't seen it, here's just one of our newer animations of the giant Magellan telescope. I also like to point out to people, this is 24 stories high, the dome, and it rotates and moves. And people often ask me, well, these things are very expensive. Yes, it is very expensive. Imagine a 24-story building. And they're one of a kind. You don't go to Amazon and buy a GMT, unfortunately. And so they're very expensive, and we have hundreds of people working on these telescopes, but they're going to be super exciting. I also point out that we normally would not have the telescope open during the day, but it doesn't look as exciting at night. And this will once again be at our Las Caponas Observatory in Chile, so we're very excited. We're hosting that at Carnegie. And these will hopefully be online within the next 10 years or so, I would say. Now, I've just told you about the James Webb, the Vera Rubin, I just showed you the GMT and some other things. It sounds like there's a lot of excitement ahead in astronomy for the next 20 years. My next talk should be super exciting in 20 years. So why is my colleague Martin Elvis writing a paper that says, is the golden age of astronomy nearly over? And the reason he's saying this is because all these facilities I just described to you are exceptionally expensive. You may know the James Webb, as exciting as it is, and it's super exciting and worth every penny in my mind, is a $10 billion project. That's an expensive telescope. The giant Magellan telescope, these other ground-based telescopes, will be of order $1 to $2 billion each. These are expensive things. And when you have limited money, this means you can't do everything. What we were able to do over the last 20 years, as I talked about at the beginning, was we had these great observatories that covered the entire range of light. We can't really do that in this age. And so, in fact, the James Webb has pretty much eaten up most of the budget for a lot of the space telescopes we would be launching. And so, in fact, we have great ideas in astronomy for the next generation X-ray telescope called LINX. This is a super exciting mission called LISA. LISA will be a space detector. It's a space LIGO, basically, to look for gravitational waves, but it's designed to look for the merger of supermassive black holes, not those stellar ones like LIGO. And then LUVOIR, in some sense, is the real follow-up to Hubble, in that it's an optical ultraviolet telescope like Hubble. It's just a bigger version. All of these telescopes are right now projected for the years 2040 or so, and that's pretty optimistic. So my guess is if I am here in 20 years giving a talk, I'll be saying, look at these exciting things coming in another 10 years or so. They're just so expensive and there's such limited resources that really, it is true we won't be able to do everything. But I would argue that doing a few things really, really well, like James Webb is going to do, or like the GMT is going to do, is really going to allow us to discover all new things. Sometimes you can't have it all. And so I think we just have to live with that and understand. But I think there's still so much more astronomy to do. So I will close here and say the past 2 decades really have been the golden age of astronomy. It's been an exciting time to be an astronomer. And with this new generation, I'm pretty convinced the next 20 years will be equally exciting, even if we don't cover every potential wave band that we've had in the past. It should be super, super exciting, so stay tuned for that. Thank you. Whoops. All right. Okay. Now I really am ready for bed. Okay. Are there any questions, however? Wait, let's see. I think we had, I think we have microphones, so are people where are the microphones? There are microphones. I see one there. Oh, and there's one there in the corner. If you don't mind coming and asking the question, that way people at home can hear it. Or if you can shout it, I can repeat it. Edmund.
So I hope these don't sound like they're coming from a really ignorant novice, but 2 questions. One was at the very beginning, you were talking about the years, how far, the billions of years we could go back, and you made one statement that caught my attention where you said, yeah, but this was before anything had formed, or something to that effect. And I'm just wondering, was there that moment where there was nothing?
Oh, that's not a terrible question at all. The answer is yes. There was the nothing, which was right after the Big Bang. There was nothing in the sense of no stars or galaxies in that sense, certainly. And in fact, at the beginning, it was just energy. So there really was a period that was nothing. I think I was referring, however, to Earth not being here, I think. I probably said it wrong. But what I meant was that we were not here at that time when those existed. But yeah, at the very beginning of the universe really was effectively just energy. Now, that's not nothing. It's just not things in the way you're thinking of it.
Fascinating.
Yeah.
And then my other question is just when you talk about, can you hear me out there?
Yep.
When you talk about gravitational waves, and then there was a moment where you had the Earth kind of waving around and stuff, and I'm just wondering the effect of the gravitational waves of things like you and me and Earth.
Oh, yeah, so that's why I love that, I mean, the LIGO team is the one that produced that thing, and I love it because it's so dramatic, but the abilities, the things they're detecting are far smaller than even the atoms. The motions are so incredibly tiny that they're really having no impact on us, thankfully. That's why it's so exaggerated. I just think it's pretty hilarious that they did it, and I always like to include it in my talks. But it really is and it's really truly remarkable that they're able to see such tiny motions. Imagine motions that's 1/10,000th of an atom. I mean, that's incredible. An atom nucleus. That's just incredible. I mean, honestly, I think most of us thought they'd never be able to do it. And so, they won the Nobel Prize fair and share for that. I mean, that was really no question.
Thank you. Fascinating.
Yeah.
Thank you.
Absolutely. Anything else? Oh, I have some over here. Okay, sure.
Yeah, so my question is, you had the chart up there with all the various telescopes as they got better and better, looking further back in time after the Big Bang. About
Yes.
200 million years after. What's it going to take to get back to the Big Bang or just right after it? And would that be radio waves, since you were talking about the redshift? And so radio waves would be even more redshifted than infrared. And can we do that on Earth, or does it have to be up in orbit, or what?
So that's a really great question. James Webb will be able to see some of the first stars, most likely. But prior to the stars, there was, in fact, hydrogen gas. And so for that, you really do need to go to the radio. So the answer is those experiments are going on. And so the furthest back, you really will need to go into probably the radio to see the gas before the galaxies formed. But James Webb should be able to very routinely get to those places well beyond what Hubble, well, not well beyond, there's not a lot of well beyond, but we'll get beyond where Hubble is. So Hubble, in terms of seeing stars and galaxies, the infrared will be fine, but the radio will be key to see that first gas.
So how close can we ever get to the Big Bang, do you think?
I don't know the answer to this, and I'll tell you that I think already we've gotten closer than we thought we would. I think people thought there was going to be a longer time period before the first stars. And what we're learning, in fact, the fact that you see galaxies at all and black holes so early on says that the universe got started much more rapidly after the Big Bang than we thought. But I actually don't know the answer. I mean, I'm not quite sure how far back I'd want to go. We're already getting much further back. I mean, when I was a grad student, we never would have imagined we'd be looking at objects at those distances. That's just 30 years ago.
Thank you.
Yeah. Oh, let's go. We can go. Yeah, we'll take back and forth. Go ahead.
All right, thanks. There have been a few papers lately that have speculated that if we had a big bounce instead of a big bang, and there's been several of them, that we build up more and more black holes each time, and black holes, including supermassive black holes, survive the big bounce because there's no point where it becomes a singularity. And would that help explain some of these early galaxies and things?
Well, it's a really interesting theory. I haven't looked at it in enough detail, but I think it's quite likely that the supermassive black hole, a related idea is primordial black holes. So your idea here is that you're recycling black holes, I guess I would say, right? That the idea here is that the universe has had multiple big bangs. It comes back down to a crash or something and starts over again. That's kind of that idea. And that in that process, somehow the black holes survive, and this is way beyond my expertise, so I don't know about that. But I will say that the fact that we're seeing these supermassive black holes so early on does suggest that maybe there's some primordial black hole seeds or something that is kind of left from somehow was there at the very, very beginning. And I think people were kind of very skeptical of that initially, but the fact that we're seeing these, a billion solar mass black hole so soon after the Big Bang really suggests you need some very accelerated process. So that's entirely possible. Yeah, that actual model sounds pretty cool. I have to see. I don't know. The other question, a lot of times people have very interesting models, but there's no way to predict. There's no way to study it or observe it, and then I'm less interested in it. So I'd be curious. I have to see if there's any observables from that particular scenario. That's pretty cool. So I think we have an online question, maybe.
Yeah, we do have a question from our online audience. Niels wants to know, what gap in observational capability would you most like to fill?
Oh, that's a great question. So did everybody hear that? Oh, wow. That's a really interesting question. I think for me, the big thing we're going to try to do over the next couple decades, and it's not something that I personally work on, is studying exoplanet atmospheres. And so I think to look potentially for signs of life, of course. And I think that experiments in something that in that realm would be very interesting. We are trying to design instruments to do that. I think I'm a very big optimist. I give lots of talks about how I think we're going to find life in the universe in the next 20 years. I say that all the time. That's probably very optimistic and naive, but I like it. I think it's exciting to think about it. So I think there must be something in that realm. There must be some improvement one could make to really study exoplanet atmospheres. I don't know what exactly it would be. I guess you would do it from space with you'd want a GMT in space. That's probably what you need to do it. A big telescope in space would make that a lot easier. That's probably the answer. I don't think we're going to see that in my lifetime. Right, it took 30 years to get the James Webb. I didn't point this out, but the James Webb telescope is the same size as our Magellan mirrors that we have, our current telescope, not the GMT. So it's much, much smaller than one of the 6 mirrors. And that's still hugely expensive and hugely impressive. So to launch a telescope like GMT into space I will definitely be retired. if alive. Sorry, you did.
Yes.
Hi,
Great talk. Thank you so much. I'm trying to understand when we talk about a black hole and that the gravity is so strong that light can't come out, but then I'm picturing, the Earth and the moon in the space-time fabric. When we talk about a black hole, is it that it's so deep that
Yes.
I mean, this concept that it's so the gravity is so strong that the light can't come out kind of sounds like a vacuum cleaner to me. But when
Yeah.
I picture it as in the fabric of space-time, it doesn't fit that way. And so how do we reconcile this?
You actually are right. It is effectively infinite in space-time.
That it goes down into it. Okay.
Yeah.
All right, thanks.
Yeah. Don't ask me what happens. Then it's out of my realm at that point. And I've worked on black holes a lot, but only the observations of them. The theory is very complicated.
The image you
go ahead.
showed with Sol in the background and Earth in the foreground, was that an actual photograph or is that a composite?
Oh, sorry, one more time. I missed what you said.
Oh, sure. Let me unmask
Yeah,
here.
go ahead. Yeah.
The image you had with Sol in the background and Earth in the foreground, was that an actual picture or is that a composite? Photoshopped.
Oh, I'm pretty sure it was. Oh, it was the next one. Those are all fake. Yeah.
Oh, okay.
Yeah. And
Thank you.
It's very, very challenging because, of course, we really want people to get excited about exoplanets. If you saw the real data, it would be exceptionally boring because all we really see, in fact, so when we do this transit method I talked about, is you really just see a little blip in a curve, and then there's an exoplanet. It's super exciting that there's an exoplanet there and that we can detect it, but you can never really see things. Now, I shouldn't say never because one of the hopes is that there are some ways of learning something about the surface of some nearby exoplanets. I think, once again, maybe in 20 years, somebody will be standing here saying that they've done that. That'll be super exciting. But almost anything you see in exoplanets is a drawing or a fake, yeah, unfortunately.
Thank you.
Yeah, that's the way it goes. Anything else? Nothing else? Excellent. I really appreciate it. I know I talked a really long time, so. Hope to see everybody in 2 weeks for Alan Dressler. Thank you. Okay.